Right, so figure 1 below shows a child on a play toy. So when there is a force applied to a spring, for example, that is an elastic material, this can do three things. It can bend, it can stretch, and it can also compress, also be compressed. In this scenario, the child sitting on the horse is going to provide a weight, so the weight of the child is going to be the force applied in this one. Okay, let's see what they are asking. Spring have been elastically deformed. Explain what is mean by elastically deformed. Elastically deformed mean when a force is being applied, the object change shape, and when the force is being removed, the object goes back to its original shape. In this case, the spring change shape, in this case compressed, when the child sitting on it that means the weight of the child causing the spring to change shape, and it will return to its original shape when the force, the weight is being removed. Okay, so that is the 2 marks questions here. So when the child sitting on it, the weight of the child, the force, is going to cause the spring to change shape, and when the child gets up or the force is being removed, the spring is going to go back to its original shape. The student investigated the relationship between the force applied and the spring and the extension of the spring. So any experiments, we will have these variables chimed. So in this experiment, we are changing the force. So force is our independent variable, change the independent. And we are measuring the extension. So extension is our dependent variable. And they would ask a control variable as well. Control variables are the variable that we keep the same in order to make the test fair. In this example, we can keep the temperature, which can influence the result. Temperature is the constant, and use the same spring. Okay, so let's see what the question is asking. Okay, so the force is represented in our y-axis, and extension in meters is represented in the x-axis. This is a quite different scenario than any other graphs that we draw. Normally we have our dependent variable on our x-axis and independent variable on our y-axis, but only for this particular experiment we have that other way around. Okay, so describe the method a student could use to obtain the result given in figure 2, and you should include a risk assessment and one hazard. Okay, so what can we do to gain those kind of results? So remember, we done this experiment. So we have a clamp stand and a clamp, and hang a spring, and then we have another stand to have a meter ruler attached to it, and when we hang different set of weights onto it, and we can measure the extension, and we can draw the graph. So you need to write this in a logical step. So what can you do for the first one? You can set up a clamp stand with a clamp. So set up a clamp stand with clamp. Second one, after that, what you can do, hang the spring. So you can hang the spring from the clamp. After that, what you can do, you can use a second clamp and a boss to fix a meter ruler alongside the spring. And you need to establish where you're going to read the original length. So every time you read the length, you're going to read it from the bottom of the spring. So record the ruler, record the meter ruler, reading that is level with the bottom of the spring. So that is going to be our original length. That's going to be our original length. And then after that, what you're going to do, you're going to hang 1 Newton mass on it. First, let's start with 1 Newton. Hang 1 Newton weight from the bottom of the spring. So hang 1 Newton weight from bottom of the spring and measure the stretch range. Measure the stretch length. From that, we can calculate the extension. So how do we calculate the extension? So basically, you just take off your original length from stretch length. So calculate the extension by extension is equal to stretch length minus original length. Okay, so and what you have to do, you have to repeat this for different sets of weight. Okay, so repeat step 3 to 7 for 2 Newton, 3 Newton, 4 Newton, 5 Newton, and 6 Newtons. And then what you can do, you can record the plotter graph and plot the force against extension graph. Okay, that would be a model answer. And also make sure, don't forget to mention about the risk and risk assessment. So hazard, what is a hazard involving this experiment? The clamp, any of these clamp, either clamp, stand, or stack of masses, weight, any of these can fall into your feet. So might fall. What is a risk? It can injure your foot. So how can you mitigate this thing? Make sure to attach the stand to the desk. Okay, so we can attach the stand to the using a G-clamp. Other hazard is the spring can snap. So other hazard is the spring may snap, might snap and get into your eye. So what is the risk involved that? It can injure your eye. So what is the mitigation? You have to wear safety glasses. Wear safety glasses. Okay, right. So this one, another equation they are asking. So force is equal to spring constant time extension. Luckily for you, they will give you this. So that is an easy mark. Another thing here, So they are asking you to determine the spring constant. So force is equal to spring constant times extension. So K is equal to F over E. And force is in your y-axis and your extension in your x-axis. So if you find the gradient, that is going to be your K. So I'm going to get this point because it's nice and easy. It's 4. Right, so let me have this. So change in y value over change in x value is our gradient. Change in y value is 4 minus 0 is 4.0 Newton. And 0.10 times minus 0.00, that is 0.10 meters. So K is equal to F divided by E. So my F is 4.0 newtons and my extension is 0.10 meters. If you do that correctly, you would get 40 Newton per meter. Okay, right. So last question. Extension of the spring is directly proportional to force applied to the spring. Describe figure 2 supports, how it supports it. Okay, so figure 2 supports it because it is a straight line. Okay, that is a straight line. Also, it is going through the 0, 0 origin. So it is supporting it because the line of best fit is a straight line through the origin. So the first marks, I think it's a 2-mark question. So the first marks is for saying it's a straight line, and second marks for origin. Origin means 0, 0 coordinate. Okay, right. The last question is the student repeated the investigation using a different spring constant is 13 Newton per meter. So that means 13 Newton per meter means that spring constant, in order to get a 1 meter stretch, you need to apply 13 Newton force. Or in order to compress the spring by 1 meter, you need to apply 13 Newton force. Right, so calculate the elastic potential energy. So people confuse this equation. EE is equal to half KE squared is the equation. You will be given this equation. So people always confuse with these two equations. So you need to choose which one to use. Okay, so and also the extension is given in a centimeter, but the spring constant is given Newton per meter, so you need to convert that into meter. So for that you will divide that by 100, 0.20 meters then. So if we apply, input your formula first, half KE squared, and next one half times K is they have given 13 Newton per meter, and E is 0.20 meters squared. Make sure to show this step. Always they give you marks for it. And then if you solve that in your calculator, you should get, let me see. So you should get 0.26 joule. So 0.26 joule.